here on the left side, we have a little schematic of what happens is if there is a cut in a vessel, obviously this can lead to blood loss. And even if we think about a small cut, if it keeps losing blood, eventually it can add to a significant amount, and that cannot happen. So we have, and we can see in the lower portion of the left sort of drawing, that there is a plug that has been formed by the red blood cells in red, by the platelets in this, so they look like little spikes in grayish, and by this mesh, this wire that wraps everything and keeps everything together, that is the fibrin. Now, on the right side, we can actually see a clot that is plugging a hole in the vessel. And we can see that again, these are colors that are rendered on a computer. The original photograph is actually black and white, gray, in grayscale. But we see the red blood cells, and we can see that are all clumped together. We can see some platelets, we can see the fibrin, and we can see the hole that is plugged in by the clot. Now, here is another representation of a clot that is plugging a breach in the vessel wall. And if you see above the picture, I put a name to this. This is called the extrinsic pathway. And the title of this slide is How Do Blood Clots Form? Because the blood clots may form if there is a damage to the vessel wall. However, we know that if we take blood and if we put it in a tube, in a whatever tube, and we leave it there, after a certain amount of time, probably 10, 15, 20 minutes, the blood clots. But there was no damage to the vessel. There was no trigger from the vessel wall there. So there must be something inside the blood itself that even if there is no cut, it triggers the formation of a clot. And this system is called the intrinsic pathway. Now, this is important because we know that clots may form in situations where it should not form, where there are no cuts. And Wirkows, who was a pathologist in the second half of the 19th century, described the elements that he thought were underlying the formation of clot, whether there was or not a damage to the vessel wall. So we can see here that there are three main elements that are promoting the formation of thrombus, the triangle in yellow. And we have the vessel wall abnormalities. So even if we don't have a cut in the vessel wall, there may be abnormalities such as inflammation that promote the formation of a clot. Then there is on the right side with the green circle, the hypercoagulability, the abnormal blood constituents. This is what we're going to talk about today. And then there is the sort of blue circle that says abnormal stasis, meaning decreased blood flow. That's why we tell our patients, if you are on a plane or if you are immobilized in bed, you have a higher risk of clots. You have to move around. So these three elements that Wirkows identified over 160 years ago are still valid. And those are the three elements that we have to keep in mind. Now, this is a video that is going to show us in a couple of minutes what happens when we have a damage to the vessel wall, but also will show the clotting, or at least parts of the clotting that occurs when there is no damaged wall. So we're going to look at the extrinsic pathway and the intrinsic pathway. Let me know if you have a hard time hearing. I'm putting the highest volume possible here. And it starts.
At the site of vessel injury, the first platelets arrive to start sealing the wound. Simultaneously, the coagulation cascade with its various coagulation factors is activated. This involves two pathways, the extrinsic and the intrinsic pathway. Extrinsic activation begins with now exposed molecules of the vessel wall, such as tissue factor, which forms a complex with factor 7. Finally leading to the activation of factor 10. This factor 10A is the point at which the extrinsic and the intrinsic pathways of the coagulation cascade meet. The intrinsic pathway consists of various coagulation factors activating each other in a chain reaction. At its end, a complex with an additional cofactor is formed. This complex now activates factor 10. Since the two pathways merge at the level of factor 10A, this factor has a pivotal role in the coagulation cascade. Further down the cascade, factor 10A, in combination with 5A, activates thrombin and induces the so-called thrombin burst. One molecule of factor 10A can catalyze the formation of 1,000 molecules of thrombin. These large amounts of thrombin cause the further activation of platelets and the enhanced formation of fibrin. Fibrin then forms strands, making up the mesh that stabilizes the platelet plug in an arterial clot and holds together the red blood cells in a venous clot. It can be concluded that the central role of factor 10A in the coagulation cascade makes it a viable target for therapeutic intervention in pathologically altered blood coagulation.
Okay, I hope everybody was able to hear and understand well the video. And now I'm just here in this slide, I have sort of put a little bit of a sort of more detail on the two pathways. So on the right, we have the extrinsic pathway, the one that is activated when there is a damage, a cut in the vessel wall. And then, as you can see on the left, there is the intrinsic pathway, the one that is activated independent of the presence of a cut. And as you can see here, there are a number of factors. I'm not going to put a lot of details in this, but I'm going to highlight one factor that is called prothrombin. This is because you will see later on, this is one of the factors that genetically can predispose to the formation of clots. Also, I'm highlighting factor 5A, which is also one of the factors that can be genetically abnormal and that can predispose to the formation of clots. And I'm going to talk much more in detail later on. Now, as you saw earlier, the activation of the clotting system is a sort of a self-amplified system. So if there is one initial platelet that starts the process, soon thousands and thousands of platelets will join. And each and every platelet starts promoting the activation of these clotting factors. So there is a really exponential growth of the clot. And if the body had no mechanisms to control this, within a few seconds, most of our blood could be coagulated and we would die instantly. So besides having a very powerful clotting system, we have a very powerful clotting control system. And this clotting control system consists of three main proteins. One is protein C, and as you can see here, protein C is modified by this complex on the right, above the writing endothelial cells. There is in blue thrombomodulin, and in purple is thrombin. So what happens is the thrombin, that is this molecule that is formed during the coagulation cascade, itself controls the coagulation by activating protein C. And on the right, you can see that there is an APC. Now, I am highlighting protein S because also protein S is a necessary, we say, cofactor. It helps the activity of the protein C. And as you can see in green here, we have this APC that stands for activated protein C. And then we have on the left the factor 5A, the one that I mentioned earlier. So activated protein C inhibits factor 5A. And this is a very strong inhibitory effect that also is one of the possible abnormality at the genetic level.
Dr. Campia, can I ask you a question that we just got in over the chat function?
Yes, please.
So when we're talking about blood clot formation, typically how long does it take for something like a DVT to form?
So a clot can form in a matter of a few minutes. So we can have clotting that can occur really very rapidly. Now, with regards to a DVT that provokes symptoms, we have to consider, as we are describing it now, that while we have a clotting system, we have a very active anti-clotting system, the protein C, protein S, and now the third one that I'm going to describe soon is antithrombin. So this system is very dynamic. So it depends on the balance between the promoting factors that sort of lead to a clot and the strength of the anti-clotting factors. I would say that we have had evidence of clotting within significant clots in minutes, but probably clinically is a more dynamic process. A clot may form, they may shrink a little bit, may grow later on, so it can take probably hours or days.
Very interesting. Thank you.
Sure. So in this slide, we have antithrombin. In the past, it was called antithrombin third. And this is one of the other factors that is present in the blood that keeps the coagulation under control. As you see, there are different sort of arrows that come off the antithrombin, and it blocks factor 10A that we saw is one of the factors in the extrinsic pathway. It blocks thrombin, which is part of the sort of common pathway. It blocks the cells that can also promote inflammation and promote clotting. And also you can see here that it promotes the release by the endothelial cells of anti-clotting factors. So antithrombin is one of the other important controllers of clot formation. And also we know that genetically there may be people that have antithrombin deficiency, and this may lead to an increased clot. And again, I have highlighted it with a red circle or oval just because this is one of the 5 main genetically or genetic thrombophilias that I will talk about. Now, we can, after having a sort of overview of the clotting and anti-clotting system, I want to talk briefly about the concept of what is a inherited thrombophilia. Thrombophilia comes from two Greek words. So thrombos, the clot, and philia, that means predisposition. Literally would be friendship. That means that they are predisposing the formation of thrombus. And so the term inherited thrombophilia refers to several genetic risk factors that predispose individuals to developing venous thromboembolism. I'm saying venous because most of the times the genetic predisposition or the genetic thrombophilia cause clots in the veins. We have some acquired thrombophilias, meaning some situations in which the body produces abnormal substances that promote clotting in the arteries. But we are not going to talk about those tonight because they are not genetically, they are not inherited from our parents. Now, among patients with DVT or venous thromboembolism in general, this is in a Caucasian population. In our population, we don't have the same numbers, but the concept is that a high number of them have an inherited thrombophilia. And if we take similar people that don't have a thrombus like DVT or a PE, only about 10% have one of these genetic abnormalities. So, which are the most common abnormalities? And we can see here on the left column the condition, the factor V Leiden. Factor V Leiden. Leiden is a town in Holland where they discovered this genetic abnormality. And this genetic abnormality, we'll see later on, is also called activated, or is one of the conditions that cause an activated protein C resistance, meaning the factor V that should be easily blocked by the activated protein C is not sensitive to that action. And because of historical reasons, this is the most well known, but also is the most common. And as you see in the column on the center left, it's about 3 to 7% of the population have it. But again, it's mostly in Caucasian. It's not as common in other populations. Let's say in African Americans, it's about 1%. Now, if you have this factor V Leiden, how bad is it in increasing your risk? It's not really too bad in the sense that you see this relative risk percent-wise about 4%, meaning that compared to someone who doesn't have it, there's only a 4% increase, meaning that out of 100 people that don't have it, compared to the 100 people that don't have it, 4 more people that have it will have a DVT. So it's not very a high risk. Now, and we can see the relative risk. This was the one that I was comparing. Compared to 100 people that don't have it, only about 130 have it. So it's about 30% more. Now, the second condition, this prothrombin G2021-0A, is less common, but still is one of the two most common. And the risk is not very high. And if you have a first DTE, but if you have it and if you have had a clot, you have a somehow higher risk, but it's not very, very high. Now, if we look at protein C, protein S, and antithrombin, this is an older way to call it antithrombin third. Now we call it just antithrombin. the relative risk compared to factor V Leiden and prothrombin is much higher. So these are rare conditions that may give a higher risk. And so if you've had a VTE or so a clot in the legs or a clot in the lungs, you have a higher risk of having a recurrence. But still, we are not talking about very high risk. Now, what are these genetic mutations? The factor V Leiden is a single point mutation in the genes that codes for the coagulation factor V. So basically, single point mutation means that only one amino acid is changed in this sort of protein, but it's enough to change the shape so that the activated protein C is not really able to stop it, to hold it from exerting its activity. And if you see below, it says account for 92% of cases activated protein C resistance, meaning that there are other mutations, much, much less common in the factor V that can render it resistant to the activated protein C. And you see below it, activated protein C APC resistance is an independent risk factor, even in the absence of factor V Leiden, meaning that it's because of some other rare mutation. Then this prothrombin G2021A, 0A, the mechanism is not very clear, but what we think is that it causes higher levels in the blood, higher concentration of this precursor of this clotting factor, and that's why you have a higher risk. Now, protein C, protein S, and antithrombin have many, many possible mutations that can occur, and all of these mutations, and we will see later on, have what we call an autosomal dominant pattern, meaning that if one of your parents has it, you have a 50% chance to inherit that abnormality. And the same is for your siblings. So in a family, let's say, of 4 siblings, 2 are likely to have inherited the abnormal genes and 2 are not likely. Now, if we look at a group of people that have had a venous thromboembolism, about a third of them actually, and you can see it with the 33% in pink, have factor V Leiden. About 20%, 18% have the prothrombin G2021-0A. 32% really have unclear cause. We can't find a or a known factor. About 5% have deficiency of prothrombin C, 5% have deficiency of prothrombin S, and 5% have antithrombin deficiency. And the other 2 are very unusual, very rare. Now, we come to the more, I would say, relevant part besides the background to understand. So if these thrombophilias predispose to clots, shouldn't we all get tested so that, if I have thrombophilia, I want to know because I want to do something about it? Unfortunately, things are not as simple as they may seem. And screening in the general population is not recommended. And this is for reasons that are not specific to these clotting factors, to these genetic abnormalities, but for the fact that these the screening is worked in specific conditions. The first one is that you have to have a lot of patients that are affected, that have symptoms from the abnormality, from the genetic abnormalities. And as we saw, if we take a general population, not many patients, not many people in the general population likely develop a venous thromboembolic event or a clot or a lung clot. Now, even if you have this genetic abnormality, it's not very likely that you will develop a clot. So, what is the point of checking for something that is not going to cause trouble? And also, even if we test for this abnormality and we found that it's there, we should, and the patient has never had a clot, we don't know when the clot is going to happen, and we should have a treatment that is a lifelong treatment that we know that is safe, is cost effective, and that doesn't have side effects, because you can prevent one bad thing, but you may cause even worse problem. So let's say a patient comes and says, my sister had a DVT and has thrombophilia, one of those conditions that were mentioned. Should all family members get tested? And again, this is not a clear-cut answer. As I mentioned earlier, thrombophilias are autosomal dominant, so about 50% of relatives in a family will have the same abnormal gene. But while in theory, knowledge of the genetic defect would permit the use of a long-term anticoagulation to prevent, there are no data that support the use of this strategy. As I mentioned, we don't know if it works, we don't know if it is safe, and we don't know if the risks are higher than the benefits. However, we have to use our knowledge, because in specific high-risk situations, let's say a patient that has a genetic abnormality and has a big trauma, or has surgery, or is immobilized for a long period of time for an illness, let's say pneumonia that puts you in bed for a long time, or a patient that is a woman that is pregnant or is delivering a baby. In these situations, prophylactic treatment for a limited amount of time may be considered, because the short-term use may confer benefits that are higher than the risk, let's say, of bleeding. So are there other benefits of screening? And again, we need to use our good clinical judgment and our knowledge. And there are benefits. So in patients that have two abnormals, the same defect that is inherited by both parents, or two different defects, you may have a factor V Leiden and a protein C deficiency. In this situation, the risk of having clots is higher, and it may be, patients should be considered for prophylactic anticoagulation in high-risk situations, as I mentioned before, surgery, trauma, delivery. Also, protein C deficiency is associated with a rare but very disfiguring and possibly fatal complication of the use of warfarin as a blood thinner. And this condition is called warfarin-induced skin necrosis. In this case, to prevent this condition, when you start on warfarin, you know that you have to give another blood thinner at the same time. And if you don't know, and I've had patients that unfortunately were starting on warfarin, and we didn't know that they had this protein C deficiency because they had not had a DVT before, or their family didn't have a DVT, and they have developed these dangerous and potentially fatal condition. And in that case, knowledge could have prevented the occurrence of this complication. Now, it's also very important to know that women who have antithrombotic deficiency, they have a particularly high risk of clotting during pregnancy and immediately after pregnancy. So anticoagulation, with LMWH stands for low molecular weight heparin. The heparin shots that people that have DVT take, on the belly. and they should be treated with low molecular weight heparin to prevent or to reduce the risk of thrombosis. Now, a patient usually has a DVT or a PE and is concerned, should I be tested? And it is accepted consensus based on all the consideration that we have discussed before that evaluation for a hypercoagulable disorder in an unselected patient with a VTE is not warranted. Why is that? Because, again, VTE may be due to another cause, and even if we determine that there is a predisposing factor, it's not going to change the treatment that we do. However, we can consider testing in specific population, and this testing is available and is mostly reliable in experienced centers. So the populations are patients with a family history in the first-degree relatives, a brother, sister, one of the parents, or one of their children, and the history of a clot before the age 45. This is because the older we are, the higher the risk is because we have other risk factors. We have diabetes, we have high blood pressure. When you're younger, it's less likely. Now, also, it is appropriate to test patients that don't have a family history if they present with specific scenarios. First is young age. If patient is less than 45 and has a DVT out of the blue, that is a little suspicious that there may be a genetic abnormality that predisposes and then should be tested. Or patients that have recurrent thrombosis, they've had clots one after the other despite treatment, then we should consider the testing. Or that have thrombosis in multiple veins. Let's say they have thrombosis in the right leg, the left leg, they have thrombosis in the calf and the leg. Or in unusual veins that normally are not areas that form clots. Mesenteric, these are veins of the gut. The portal, which is the vein that brings the blood from the gut to the liver. The hepatic vein, one of the livers in the vein. Or veins in the brain, in the skull, because normally they are not frequently affected by clots. Or patients that have a history of warfarin skin necrosis. As I mentioned earlier, this would be highly suspicious for a protein C deficiency. Now, I've given a sort of 1 mile high overview. I hope that I have answered some of your initial questions and that I have at least given some clarification of what these inherited thrombophilias are. But I know that there may be many more questions that you have and that I have not addressed, and I will be happy to address them now. And I appreciate your attention. Thank you very much.
Thank you so much, Dr. Campia. That was excellent. That was actually the first time I've had somebody try and explain the clotting cascade to me, and I got something out of it. So well done. We did get several questions submitted over the chat function. So I will go through those, and then if we have time, I'll try and unmute the lines. We tend to get a lot of background noise just because we have a lot of people on the call, but I will try and unmute the lines and see if we could do that for a few minutes as well.
Sure.
But one question that we had was a woman who is heterozygous for factor V Leiden, and she has 2 sons. Is she someone that should consider her sons getting tested, do you think?
Well, the issue is, as I mentioned earlier, if there is no history of clots in any members of the family, the common recommendation is not to test. because of the fact that we would not be treating anything, and sometimes the idea of having a genetic abnormality can affect the perception of the children. So they say, "Oh, I have something wrong in me," and many times that can trigger concerns. It can drive a lot of sometimes a lot of additional testing that is unnecessary and possibly risky. So, as a general rule, if there is no family history of thrombosis at an early age, less than 45, there is no recommendation to do the testing.
Now, what about in patients? We have a couple patients who said that they've had multiple blood clots and they have never had any sort of genetic testing. Would you ever do genetic testing just to kind of satisfy your curiosity?
Well, I would say that there is a relative indication in testing genetically, because, as I mentioned, some of the genetic abnormalities may be relevant for specific condition. Let's say deficit of antithrombin may be relevant in a woman who is of childbearing age, and knowing that in the family there is that mutation, and that mutation has led to repeated events of venous thromboembolism, that I think would be a appropriate genetic testing. It just be out of curiosity probably would not be, in my opinion, a reasonable justification. And in that case, if a patient has a concern, I would recommend to talk with a specialist, a vascular specialist or a thrombosis specialist, to see if there are stronger reasons to do the testing.
Okay. So we have a gentleman who has had two blood clots, a DVT and a PE. He had the DVT, which was provoked from an ankle injury and then long flight, he believes, and then the PE was unprovoked. And he's concerned about his daughters, who are either on birth control or considering starting birth control. Is there, since birth control can be, increase your risk, is there a reason for them to consider genetic testing?
Yeah, this is a very relevant question, and many times this is one of the most pressing questions. As a general rule, we don't recommend to test for genetic abnormalities in a woman who wants to start the use of contraceptives. However, if there is a strong family history of DVT or PE, as in this case, particularly an unprovoked situation, having a genetic testing may indicate the presence of a predisposition that would potentially alter the type of contraception that the woman decides to have. So I would say that in this case, it is reasonable because it can guide the type of contraception. Instead of using the standard estrogen treatment, there may be treatments that have lower risk of clotting, or there may be treatments that are really safe that and effective without the risk of clotting.
Okay, very good. If a person has had genetic testing and they do come back with something that they're genetically predisposed to blood clots, what lifestyle modifications, if any, do you recommend that they make?
Yeah, this is very important. In general, lifestyle modification, because our recommendation for any patient, independent of the predisposition for clotting and independent for the presence of a genetic abnormality. We know now that clotting is triggered by inflammation, and a lifestyle that is rich in oxidants, such, or I would say rich, that is unfortunately exposes to oxidants such as smoking, bad diet, obesity, sedentary lifestyle. Those can all promote, but we don't have any study that can quantify, is precisely quantify the contribution of these factors on top of a predisposing factor. So I would encourage anyone to consider a healthy lifestyle, and in particular those who may be at an increased risk of clotting.
Okay, terrific. Let me see any other questions. I just want to make sure that I didn't miss any. So in terms of the future of, genetic testing is a rapidly evolving field, is there any exciting work that you know of being done in terms of genetic testing for people, with blood clots, or to see if people are at a risk for blood clots?
And I would say that I'm not aware of any major breakthrough that are in the pipeline. We are able to have more reliable tests now, particularly for rare conditions. But because they are so uncommon, the the availability of newer tests probably is not going to have a major impact on the larger population. With regards to testing, I would like to expand in areas, we have a few minutes, that I didn't focus on specifically, is the fact that many times testing should not or cannot be done at the time of diagnosis, in the sense that a patient that presents to the emergency room with a swollen leg and is diagnosed with a clot, the process of clotting uses a lot of the factors that are present in the blood. So if, let's say, we wanted to determine if a patient has protein C deficiency, and we are testing the patient at the time when he or she presents, the protein C is probably going to be low, not because is the genetic makeup of the patient, but because the clot has used the protein C that was in the blood, and now the one that has been used is not there, is not measured. The same is for protein S and for antithrombin. Now, if the patient has an indication of being on anticoagulation, and you should not wait to do the treatment for testing for a genetic deficiency. So many times you treat the patient, and once you have completed treatment and you want to, and you have an indication for the genetic testing, then you do the testing. Now, when we say genetic testing, we should not think that in all of these conditions we are checking the gene, looking at the DNA, looking at the chromosomes. Only for factor V Leiden and for the prothrombin 20210A, those are done as genetic testing, in which we draw the blood, we isolate the DNA from the blood cells, and we look at the DNA. The other tests are tests on the levels in the blood, and that's why we cannot do them at the time of the diagnosis or when the patient is on anticoagulation.
So you're saying you might come back with a false positive or a false negative? Is that kind of what you're saying?
That's absolutely correct. Mostly false positive, in the sense that, let's say, a patient is given heparin, and heparin affects the levels of antithrombin. So the patient levels of antithrombin are going to be low because the patient has been given heparin, or the patient has been started on Coumadin. Coumadin lowers the levels because it decreases the production of protein C and protein S. So if you have a patient on Coumadin and you check those levels are low. So another important aspect is that there is no rush in doing the genetic testing, because it's not going to change our management. The patient that needs anticoagulation needs anticoagulation. We know that if a patient has had a recurrent event, particularly if unprovoked, the risk is very high and should be treated with a blood thinner for extended period of time, independent of the testing. And the other thing is that your genetic testing and your genetic abnormality is not affecting the success of treatment. So you may have activated protein C deficiency, or you may have antithrombin deficiency or factor V Leiden. You still get the benefit from being on a blood thinner. Doesn't matter.
Very interesting. I think this will hopefully kind of calm a lot of people's nerves. I know there's always a lot of concern, especially with parents in diagnosis and stuff, and wanting to make sure that their kids are protected. But it seems that from what you're saying, that sometimes it's not always best to know, because it can cause you to take some unnecessary risks or undergo unnecessary treatments. So that's interesting. So I had a question just come in about the protein S level.
Yes.
So it's from a woman who's had multiple DVTs, and following recommendations, her sons were tested when they were younger, and they both tested positive. She has since heard that protein S levels change as you age. Is this true, and should her youngest son also be tested?
In general, the levels of the anticoagulation proteins, to my knowledge, don't change. And if you have a deficiency of protein S that has been confirmed, there may be fluctuation of the levels, and so these may be detected. But besides the levels, we also have tests for what we call the activity of the factor. And we know that the testing for the activity is more precise than the testing for the levels. So the levels should not be considered the best parameter to follow. And most of the labs that now are specialized in these type of tests are aware of this and do the activity and not just the levels of these proteins.
So when you say activity, you mean they're looking to see if the levels are rising and falling, not just what the level is at that time.
Thank you for asking this clarification. So think about having a certain amount of an ingredient, or let's say of sugar, is how many sort of tablespoons of sugar you have is the level. Then, if you put the sugar into, a drink, and you drink it, and you taste the sweet, that is the activity. So the level and the activity are closely related, but it is more precise to measure the activity, let's say, to see how sweet a drink is, than to measure the amount. So let's say if you have a drink that has sugar, it's easier to check how sweet it is than trying to figure out how many teaspoons were put in it. Okay?
Oh,
so
okay.
the test it looks at how effective is protein S, and this is done with very sophisticated sort of machinery and fluids and standardized fluids, so that you know how effective is your protein S in inhibiting clotting, rather than saying, oh, in the blood I measure a level of 10, because that measurement is not very precise. It does not necessarily tell you, yeah, the measurement of 10 may look low, but when you test it for how good it is blocking coagulation, that is the important test.
Oh, very interesting. I like the sugary drink analogy.
Mm-hmm.
So we got two separate questions in, but I think that they kind of go hand in hand. The first part is from the same individual that asked about how long it takes the clot to form. And he is now interested in how quickly typically do clots dissolve on their own after anticoagulation therapy has been started. And then the second part to that question is, does a person who's been tested to have some genetic predisposition to clotting, do their clots tend to hang around for longer? Do they take longer to dissolve?
It's very important. So regarding the first question, it's interesting because we don't really know for sure, in the sense that nobody has really, at least to my knowledge, done a study to say, well, if we start today on this anticoagulation and we see tomorrow how big the clot is, the day after, and so on and so forth. Why is that nobody has done it? Not because people don't think about it, it would be interesting, but because the speed of dissolution of a clot depends on several factors. Depends on how old is the clot. So a clot that is very fresh tends to be more rapidly broken down by the body. One important concept: the blood thinner does not get rid of the clot. Okay? The blood thinner doesn't touch the clot. If you take a clot and you put it in blood that is full of blood thinner, the clot remains the same. What happens is that the blood thinner prevents the formation of new clot, and the intrinsic system of the body that breaks down the clot, which is called the fibrinolytic system, takes care of breaking down the clot. And therefore, the blood thinner is just preventing new clot, and the breakdown depends on how old the clot is, depends on how active the fibrinolytic system is, depending on how much clot there is, in what location it is. Is it in a vein that was completely occluded, or is it in a vein that had only half of it blocked? So, unfortunately, we don't have an answer, but at the end of the day, it's not going to change anything of what we do. So, it would be interesting, but I don't think we'll have an answer anytime soon about this.
So somebody who has a genetic predisposition, you don't know, I guess, if it causes it to break down faster or not.
It would not, because the breakdown of the clot has nothing to do with the clotting system as the formation of the clot and the sort of balance of the clot. The fibrinolytic system is triggered immediately after we start clotting. That is a separate system. And the genetic factors that we have discussed don't affect the fibrinolytic system directly.
Oh, very interesting. Well, the human body is certainly amazing.
Absolutely. It's incredible.
Yes. Well, we're just at about 8 o'clock, and we've got a lot of people on the call, so I'm hesitant to unmute the lines. I think we're just going to get a lot of background noise. So I think we are going to go ahead and wrap up with Dr. Campia. This has been so informative and really educational. So thank you so much. This was excellent.
Thank you so much for the invitation, Catherine. I'm looking forward to more educational sessions.
Excellent. Well, thank you. We'll definitely have you back. And I'm excited to announce that for August, we are delighted to have Dr.